Today we'll be discussing the structure of simple solids. Why is the structure of simple solids important? Well, it's important to the study of inorganic materials. It's important to the understanding the underlying principles and interactions that lead to preferential structures being adopted over others. And just simply stacking spheres which represent atoms already helps to provide a good intuition to more complex inorganic material behaviors. This understanding also helps rationalize the observed trends in thermal stabilities and solubilities of ionic solids formed by group 1 and 2 elements. And finally, this allows us to classify organic solids based on their electronic properties as either conductors, semiconductors, or insulators. So let's start off with, what is a unit cell? A crystal of an element or a compound can be thought of as being made by periodically repeating structural segments. As we can see here, the geometric pattern that arises from these is called a crystal lattice. So that's defining the full crystal, more or less. A unit cell is a three-dimensional area of space that contains all the atoms required to create the entire crystal by just cloning it in all directions. Think of this as the blueprint of the crystal that gets copy-pasted in all directions to form the full crystal. So over here is our unit cell, and here's the crystal structure, and as we can see, it repeats indefinitely. How do we describe crystal structures? Well, crystal structures are described by choosing the smallest unit cell possible that will create the desired crystal structure when copied. And in 3 dimensions, there are only 7 different possible unit cell compositions. These are cubic, tetragonal, orthorhombic, monoclinic, triclinic, trigonal, and hexagonal. Each of the 7 different crystal systems requires different variables to define them, which are called the lattice parameters. For example, here we can see that cubic has equal angles and equal sides, so mathematically it can only be 90 degrees, so we really don't need to define anything, but just in case we can define the angle to be 90 degrees. Tetragonal is the same, all the angles are 90 degrees, however, one of the sides is no longer equal, so we have to define an extra side length. For cubic, you have to define one side length as well, since it can scale up or down. Let's take, for example, triclinic, where nothing is equal anymore. Everything is different, you have to define all the sides and all the angles. So what is a lattice point? Well, a lattice point is a molecule that exists relative to the lattice. It is fully inside the cell. It adds 1 unit to the cell point count. So, for example, we don't have one here, but if it were to sit right there, that would add 1. If it's on the face of the cell, it adds a half. So if it sits on any of these faces, if it's on the edge, it adds a quarter. And finally, if it's on a corner, it adds a 1/8, which we can see here. 1/8 of the sphere is inside the cell. Yeah, so for example here, crystal lattice comprised of cubic systems that have atoms only on the corners of the cell will add up to, 8, 1, 2, 3, 4, 5, 6, 7, 8. Each at 1/8 adds up to 1. So how do we identify lattice types? Well, we have 3 different lattice types. We have primitive denoted by P, where the unit cell only contains 1 lattice point. We have body-centered denoted by I, where the unit cell contains 2 lattice points. And face-centered denoted by F, where the unit cell contains 4 lattice points. For example, if we want to identify the structure here, which is zinc sulfide, we can see that it has sulfur on all the corners, so that's 8 times 1/8, which is 1. Then it has sulfur on all the faces, and since they're cut in half, they only count for half. So we have 6 of them, 1, 2, 3, 4, 5, 6. So we have 3, and in total there's 4 sulfur. And the same is true for zinc, where we can see that all 4 of the zinc atoms are actually well within our unit cell. The 2 different atoms in this scenario are considered to be linked to 1 lattice point. So 1 atom of zinc and 1 atom of sulfur make up 1 lattice point in this case, for a total of 4 per unit cell, and therefore this is a face-centered unit cell. So how do we identify the lattice type of cesium chloride? Well, we can see we have 8 chlorine on all the corners and 1 cesium in the center. So the 8 chlorine 1/8 times 8, that's 1. And 1 cesium in the center, which is also 1. And 1 cesium and 1 chlorine make up our 1 lattice point. Therefore, we have a primitive unit cell, since together they are 1, and there's 1 per unit cell. How do we interpret fractional atomic coordinates? Well, conventionally, a unit cell has a dimensionless upper bound of 1 for all 3 of its coordinates x, y, and z in any direction. So, for example, let's take x along here. That's 0 to 1, y 0 to 1, and z 0 to 1. That is, like it says here, that is all the atoms within 0 to 1 on the bounds. We can make a simple representation of this by projecting the 3D structure onto a 2D surface, which helps us interpret it. Yeah, so we can choose any axis we want and look down that axis. The atoms will then have their height out of the page denoted by the parentheses beside it. As we can see here, we have tungsten in a body-centered cubic arrangement, where we have tungsten on the corners and one in the center. And then say we're looking top down, or we can look from any side here since it's symmetrical in all the axes. We can see that this representation below it here shows where the atoms are relative to what you're looking at. So, for example, 0 would be this one, if we're looking from the top down, that is. 0 would be this one, 1 would be that one, and a half would be the one in the center. And that is the same for all the corners, since it's symmetric. So how do we convert a 3D lattice into a projection? Well, for example, if we have elemental gold, which arranges itself into face-centered cubic, if we were to draw it as a projection, let's say we look down on it from above, or from any side that is, since it's symmetric in all axes, we know that we have gold in all the corners, so we can denote these as 0 and 1. And then we have gold at the top and bottom of the cell, on the faces, so that's 0 and 1 in the center. And then we have gold on all the faces on the sides, so that's a half since they sit halfway up the face relative to us. What is the close packing of spheres? Well, usually when we have metallic and ionic solids, they do not have any directional covalent bonding, and as such, the spheres that represent our atoms are free to pack as tightly together as the geometry allows them to. We have two main ways of packing these spheres: hexagonally close packed and cubic close packed. Hexagonally close packed spheres consist of one layer of tightly packed spheres with a second layer of the spheres that sit within the dips. So as we can see here, they kind of sit between the dip generated by the three spheres below it. And then this layer just repeats over and over in this AB pattern. Cubic close packed spheres are similar in that their first two layers are identical to the hexagonally close packed pattern, but the third layer does not sit directly above the first and instead sits in the dips that the second layer did not occupy within the first. As we can see, it almost looks like a sort of offset here. This pattern then repeats where the structure has those three distinct layers over and over, and it's called face-centered cubic, and this one's called hexagonal closest packed because when you define it as a unit cell, this takes a hexagonal form and this takes a cubic form. So what is the coordination number of a sphere? The coordination number in this context is just the number of nearest neighbors. In a face-centered cubic arrangement, the coordination number is 12. We can define it either as the geometric way, where there's 6 on the same level around it, 3 above and 3 below, or in the cubic-centered arrangement that we have here, where we define it as a unit cell. We can see that the one that sits on the face between two unit cells, let's say, has 4 connections, or well, 4 neighbors. In the faces of the unit cell on its left, it has 4 connections on the connection point between the second unit cell, and then it has 4 neighbors within the neighboring unit cell, similar to the one on the left. What are holes in close packed structures? Well, since our sphere model will always be unable to occupy the total volume of the unit cell, just due to the way that the spheres pack together, they will never fill it up fully and leave these small holes in between them. In a real atomic model, this isn't actually very true since electron density isn't strictly confined to a sphere, but it is still quite relevant to physical structure where we will have smaller atoms sit in these holes to form more complex lattice structures. So there are two main types of hole: octahedral and tetrahedral. As we can see here, we have octahedral holes, and they lie between 2 triangles of spheres on adjacent layers. Here in a HCP formation, we can see we've added an extra atom here just to make it a bit more apparent. This is not part of the unit cell. And we can see that between this triangle, there sits an octahedral hole here, and it's between these 2 triangles. And same here, it sits right there. In a cubic close packed structure, they sit in the same form. They sit between triangles, and it's a bit easier to visualize since it's more or less alternating, where we can take the lattice either centered at these, where then we will have this one in the middle of this sort of tetragonal structure, and these will the holes will form it, or the other way around. But by convention, the bigger atom does form it. So what is a tetrahedral hole? Well, a tetrahedral hole is formed between a triangle of spheres capped with a single sphere that lies in the dip of those triangles. As we can see here in our hexagonal close packed structure, we've only just taken 2 parts of it, and we can see it forms that triangle and sits in here. Same thing here, forms a triangle, sits there. And we can extend this further. We can see the holes are on all the sides. There are 2 types of tetrahedral hole, pointed up and pointed down. So this would be our T, and this would be our T prime, which is pointed down. And it just depends on whether the capped sphere, so for this one it would be that, and then this one it would be this one. So this would be T prime, this would be T prime, where the capping sphere, whether it sits above or below. In hexagonal close packed, we can see that the tetrahedral holes are way too close together to actually occupy it at the same time due to electrostatic forces. Like these two cannot be occupied. It's either this one or this one. So how do we determine the ratio of spheres to holes in close packed structures? Well, similarly to when we were identifying lattice types, we just count the number of spheres in each unit cell and then compare them. So, here in this case with our tetrahedral holes in a cubic close packed structure, we have the face-centered cubic, so we have 1, 2, 3, 4, 5, 6, 7, 8 on the corners, so that adds up to 1. And then we have 1, 2, 3, 4, 5, 6 on the faces, which adds up to 3, so 4 in total. And then we have 1, 2, 3, 4, 5, 6, 7, 8 tetrahedral holes fully within the structure. So there's actually 2 holes for every atomic lattice point, or whatever you want to call these. So what are the structures of metals and alloys? Well, from X-ray diffraction studies, we found that many metallic elements actually have close packed structures, which indicates to us that the bonds between the atoms have very little directional covalent character. This close packing results in most metals having high densities, as a lot of the space constituting the unit cells are filled. The elements in the middle of the D block include the densest solids under normal pressure and temperature conditions. So what is polytypism? Well, polytypism just refers to the variance in the stacking arrangement of crystals. An interesting example is in metals, where a metal will adopt one of the common polytypes HCP or CCP based on the electronic structures of its atoms. The selection of stacking arrangements also reflects on the metal's properties. For example, soft and malleable metals like copper and gold tend to adopt CCP, whilst brittle and hard metals such as cobalt and magnesium tend to adopt HCP. This behavior relates to how easily the planes of the lattice can slip past each other. In HCP, only neighboring planes can move easily relative to each other. In CCP, however, we can choose our 3 different planes in any of the 3 orthogonal directions, which allows for greater freedom of movement. Surprisingly, we are not limited to only HCP or CCP. Crystals can form infinite amounts of polytypes, more complex repetitions of different layers which allow for different properties and different sequences. Like for example, here we have ABC, ACB, as opposed to HCP, which was ABAB, and CCP, which was ABC, ABC. The main restriction we have on this is we're not actually allowed to have adjacent identical layers, so we can't have AA or BB next to each other, as the spheres would superimpose. What are non-close packed structures? Well, not actually all elemental metals have a close packed structure at room temperature, and some may even undergo a phase transition and lose their close packed structures. One of these arrangements is body-centered cubic, where there's one sphere in the center and one sphere in each corner. Under standard conditions, body-centered cubic is adopted by all the alkali metals and some in groups 5 and 6. The least common metallic structure is primitive cubic, where spheres are located at the lattice points of a primitive cubic lattice, and the only example of this under normal conditions is a single form of polonium. Some metals may actually have slightly distorted versions of simple structures. A good example of this is zinc or cadmium, which are almost HCP, but the planes of close packed atoms are separated by a marginally greater distance than in conventional HCP.